as we start 3-2 is understanding that the degree of a polynomial is based on the largest exponent that you see within that polynomial. Now, it's nice when they're in order because that makes it really easy. They won't always be, but here's what you're going to be wanting to focus on. The degree is always going to be told by that largest exponent that you see on a single term, okay? So this is just some ways that we can call them out, have names for them. Do we use the names a whole lot once we get past 3, to be honest? No. I mean, the first 3 are pretty straightforward, well, even the first 4. Constant just means there's a number here. So like, I'll just write for this one. So like if this said f of x equals 8, that's basically saying y equals 8. Okay, it's a horizontal line. Number 1 is linear because it makes a line. Makes sense. If you had like y equals x plus 2, it's going to draw a line. Degree 2, I'm just going to draw some pictures with these first couple. There's a reason for this. I'll come back to that in a bit. Quadratic just means it's squared. That's our parabolas. Okay, we've seen some of that. Cubics, we haven't gotten into this yet. It's coming. Those are going to kind of look like little snaky looking guys. Actually, that's coming today. So cubic 3, just like you cube something, is 3. The last ones here, quartic and quintic. Quartic, I always tell people, remember it's like a quarter. There's 4 quarters in a dollar or in a game. Well, some games. So that's 4. Quintic, now that gets a little trickier. That we don't reference a whole lot. Then I guess the mathematicians just got tired of it after number 5, because then we just start calling a polynomial of degree whatever. Okay? It's 7, polynomial of degree 7, and so on. And so why we have those, again, is just a way to be able to define things a little bit better. So, what does that have to do with all this other stuff? A whole lot of vocab is what this is. So we can understand each other as we speak here. So as I get to the bottom, these are not polynomials. You're like, well, wait a minute. Why not? Polynomial functions are always going to have whole number exponents. So here, if I were to rewrite this, that is not a whole number exponent. Okay? So you cannot have radical or fractional exponents. That's a no-no with a polynomial. So you're like, all right, let's see here. So we can't have fractional exponents or radicals. Oh. Well, what's wrong with these? That's a whole number. That's a whole number. Let's look at them not as fractions, though. So if I were to look at these as not fractions, I'd have x to the negative second plus x to the negative first. No negative exponents. Because again, that's going to take them out of these areas. Bless you. Oh, bless you. So I keep looking. I'm like, okay, no fractional exponents, no radicals, no negative exponents. My gosh, this sounds like parental rules. There's so many no's. No, no, no. Okay. Your base has to be x. Now, Hardy, are you saying so like it couldn't be some other variable like y or z or n or something like that? No, but it has to be a variable. I guess that would have been a better way for me to put it. Because that, again, completely different from something we're going to see with any of these. But this last one would be. You're like, well, wait a minute. I thought you said no fractions. I said no fractions on Your exponent. Your exponent is still a whole number. That's my coefficient, my number in front. So basically, everything fits into the world of polynomials except fractionals / radicals. Negative exponents, we just got to make sure the base is a variable. Everything else plays well. So, two last little pieces of vocab, and then we'll see how we're doing here. Standard form, written with the highest exponent first and in decreasing order. So you're going from least to greatest when you're looking at your exponents. And then the degree of a function is the highest exponent. I'm going to take that a little further. On one term. You don't add them all up and call that your degree. One term, the biggest one wins. And so when we look at anything that we at least think is going to be a polynomial function, we've got to look and see, okay, does it break any rules? Those are all whole numbers, okay. No negatives. That's x. Okay, this is good. This is a function. It's a polynomial. Standard form. Find the largest exponent and keep everything about that term with it. The coefficient, the sign, everything. And then we go to the next biggest one. And finally, we finish with the constant. So you can have gaps in degrees. That's okay. But you've got to work that through. So our degree, biggest exponent. The type goes with your degree. So here my degree is 4. So this would be a quartic polynomial. And you never want to figure out what your lead coefficient is until it's in standard form. The lead coefficient is just the number in front of your first term. But if you don't have it in standard form and you write 1/2, that's not right because it's not the coefficient of your largest degree term. So, I want to play with one more of these because this isn't the craziest stuff ever. So let's do this. Let's do, I'll keep life easy on you. Let's go to 3. I'm going to freeze for a minute. Try to fill your way all the way across here. On number 3 with your standard form, your degree, your type, and your lead coefficient. And then I'm going to give you a bonus afterwards with this. So you can kind of see some weird too. Am I going to give you all of the degrees and all the names of them? Is that the question? And you would guess correctly.
I hear you give your other classes like open note tests.
Yeah, because that's not ours.
Bingo!
Do you? But like, why? What's the difference?
Tell them again.
But we just move faster, so we should still get the notes.
No, that's not how this is going to work.
I did drop it last year. I dropped it this year. I just got to get through this semester.
There, we're going to get through. Okay, so number 3, largest exponent is 5. So that's where we got to start with our standard form and work our way down. The degree goes by whatever that largest exponent is. The largest exponent tells us what name we need to use for the type. In this case, quintic. Again, a weird one. And my lead coefficient is 2 because once I'm in standard form, whatever number's in front counts for that. The bonus comes with number 4 because it looks weird. You're like, there's decimals, there's radicals. Hardy, I thought that stuff was illegal. That's only illegal if it is on your variable term, like it was up here in A. Just having a radical there doesn't hurt anything. Pi is a number. That can be a coefficient. That's legal. So we put them in order. Highest degree is 2, which is a quadratic. We've played with that. And your lead coefficient is pi, because again, it's a number. It's not a normal number we see there. It's a number nevertheless. So, again, issues besides the fact that I'm not giving you the chart. Any other ones? Oh dear. Yep, I just said that. We're not giving you the chart. That's true. Okay. So when we actually get into doing something with these, instead of just using words, okay, evaluating a polynomial function. Direct substitution. We love direct substitution because it takes us back to our Algebra 1 days. F of x equals this big old polynomial. Can be evaluated at x equals 3. When you see f of and some number inside, this doesn't mean you're solving for f. It means you're dividing by 3. Don't do it. All this means is everywhere that you see an x in that polynomial, you plug in a 3 and get the answer. You can go to a calculator. You can use your noggin. You do whatever you want. So let's see here. As long as I type it in right. So it's just like Algebra 1 where it says, here's an equation, substitute in, 3 for x. Oh, okay, I can do that. It's just in a different format. It's in function notation. So keep it simple. Now, do I like the store function on the TI-84? No, I really don't, to be honest, because it takes you just as long to plug that in and then plug all the x's in and then plug enter as it would be to just type it in yourself. So, I mean, if you want to play with the store function, you can, but it can cause issues when you're doing other problems, which is why I don't. My gosh, if we can't remember at this level to put parentheses around the number we're substituting in, I don't know what to say. So I'm not playing the store function game because I think that's kind of silly. Because again, for instance, I look at one like number 6, and I'm like, really? I can't just kind of use my noggin here? I think I can use my noggin. What's the absolute value of -1? 1. So as long as I'm okay with some of my base math skills, and again, I'm hoping at this point that you would be, probably can do that in our heads. Just if you're going to do it in your head, remember, you're squaring first, then multiplying. Don't give me -8 squared. That's not going to get you to where you want to be. So whether you go to the calculator or you're going noggin mode, we still got to follow order of operations. Okay. Little stuff. You're like, okay, numbers. Hopefully numbers aren't bad. We'll see. Oh boy. Evaluate the following using function. Okay, so we have c of x and d of x. The letter in front just tells you which expression you're using. You're like, c of -2. Okay, we've done that. Then you look at 9, and you go, what the heck is that? d of 3a. Okay. 3a is the value you're plugging in for x. Yes, we're substituting a variable with another variable. So, here's my d of x. Every time you get to an x, we're going to substitute the 3a in. Everything else stays the same. Now, does that mean I just get to plug in the 3a and say, whee, I'm done? Okay, I'm going to get that x out of there. It's going to get confusing. No, I still need to simplify this. Well, Hardy, I can't put that in my calculator. You're right. So I'm actually going to take a little time here. I'm not going to go into superhero mode. I'm going to distribute my 3. 3 cubed, now 3 times 3 is 27a cubed. Squared goes through, 9a squared minus 2. And now I can do my last step and actually simplify this. So negative 81a to the third. We're just multiplying coefficients. Yes, it's legal, even with this having a squared and the other part not. 63a squared minus 2. No more like terms to put together. Get that knocked out. So again, just treat the variable term like you would any other number. It's still just substituting. It's still just substituting with parentheses. Nothing else is different. Any issues with 9? Because I want to make sure before I go to 10. Because 10's got one more twist. All these twists. So much fun. So much fun. Yeah.
Why are you just multiplying coefficients here? It's like -3 times 27 is 8.
The same reason I can that if I'm distributing and I have like 6 times 2x, I can have 12x. It's no different. Yeah, it's still just, the coefficients can kind of just play their own way with that. Okay? Any other questions? Okay. So let's deal with this crazy one. All I'm going to deal with at the start, I'm going to do this in 2 pieces. I'm going to forget about the 6 for a moment. It doesn't get to go away forever, but it gets to go away for a little bit. So we're going to the C function, this one, and every time that we see an x, this is going in. So we've got 2n plus 1 squared, x squared, minus 2x plus 1. So we got to multiply this stuff out. Now again, if from what we talked about last week, you're not comfortable doing the pattern yet, you're going to have to FOIL that out. You can't just distribute the squared. You lose terms, and that won't work. So if you remember our pattern from last week, we're going to square the first term, both parts. We're going to multiply these together. 2n times 1 is 2n, and double it. So 4n plus 1. I'm going to distribute this -2 through. And the plus 1 here is just hanging out on its own. So multiply this out completely. Distribute the -2. And once that's all done, all the parentheses have been taken care of, except the big one that all these are combined in. Go ahead. Find your like terms. So let's see here. Positive and negative 4n cancel. That's nice. 1 minus 2 is -1. Oh, plus 1. That all cancels too. Well, wasn't that fun? Everything went bye-bye except the n squared term. Now again, can you get some really long chunkers of answers? Yeah, we saw that in number 9. Sometimes it'll be nice and simple like number 10. But again, the only way this stuff gets comfortable is if you practice. Any issues on evaluating? Okay. Yeah, I'm sorry. Okay, yep. I will come directly there when we get situated, just to see if there's a little tidbit we got to clean up. So star it or something so we don't forget. No. So, all right. Properties of graphs of polynomials. Okay. So let p of x be a polynomial of degree n greater than 0. So we're not going to have negative exponents we're dealing with real coefficients. Okay. The graph will have the following properties. continuous for all real numbers. Okay, what does that mean to a normal human? No holes or gaps. Do we want an example? We do. This is a perfect example of letter A because there's a hole. That's a problem.
That's a thing.
That's a thing. Holes in graphs are a thing. We've already had holes in some places, but we'll talk about that again. Oh, we have. No sharp corners. You got it. No absolute value equations. They have sharp corners. So that's a Now, this last part, okay, C and D, this is more to assist you in doing this quickly than anything else. Has at most n real zeros and at most n minus 1 turning points. Okay. Number 13. Real zeros, x-intercepts. So I sit here and I'm like, okay, so 1, 2, 3, 4, 5, 6, 7. So just in this picture, I have 8 zeros. Like, I literally can see that. And with the arrows, I can tell it's going to keep going. But let's just do with what we can see. So, turning points are maxes and mins. So if I look at those, I'm like, okay, so max, min, max, min, max, min, max, min. Well, I already can see I have a problem. 1, 2, 3, 4, 5, 6, 7, 8. I have 9 turning points. You're like, yeah, so at most you have n minus 1. So if this has 8, I should have 7 turning points at most. Well, I didn't. I had 9. So if you see more maxes and mins than you do zeros, like in the picture that you see, if there's more of the stars, if there's more of the mountains and valleys here than there are zeros, that doesn't qualify as a polynomial function. Okay? And the last part, which is the last thing we're going to roll into today, is understanding increasing or decreasing with bound. I'm going to do that in the next section instead of trying to use one of these to explain it. This is where if we just figure out a very simple pattern, life is going to be easy. Even though this seems very abstract, most of the ones you're going to run into that are tricky with these are going to be these two. Okay? So to kind of ease up some things a little bit. But again, when we practice it, I know, isn't it crazy? That's why we're not doing the whole section in a day, because that'd be insanity. Okay. End behavior will finish us for today. I'm just looking at one thing. I don't get to show you the fun till tomorrow. That's disappointing. It is. I want to show you the fun part, but I can't do it today because we're not going to have the other stuff set. Okay. End behavior, it's exactly what it sounds like. Describes the behavior at the end of each portion of your graph. Okay, where's it going? But of course, mathematicians like to make this more complex. Instead of just saying, hey, when the graph's going to the left, it's going down. When it's going to the right, it's going up. We got to use infinity for everything. So, just a reminder of a couple of things. Remember, f of x is just a fancy way of saying y. So when we're talking in f of x or y terms, okay, negative infinity is the same thing as your graph going down, okay, to negative infinity on the y-axis. Positive infinity is the same thing as going up. So again, we're using mathematical terms in symbols actually instead of words. When we're talking about just x, negative infinity is left, just like it is normally. If you're looking at a number line, we got the arrow going left. it's negative infinity. It's going forever negative. And positive infinity means we're going to the right. The reason I want you to kind of have that there is because when we start expressing these end behaviors in math language, it's going to look weird if you don't know what the symbol actually means. So here's how this is going to work. And I'm going to go straight to the examples at the bottom, and I think we're going to be done because I think you're going to pick up on this, especially having this in mind. So here's what we're going to do. Describe the end behavior for each. Okay, let's just focus on that for right now. Every end behavior that you do is going to look like this at the beginning. Some of you are probably going to think you're going to get carpal tunnel from all this right. You will not. Okay. Here's all we're paying attention to when we're doing end behavior. Two things. That arrow and that arrow. So let's speak this out first without the fancy language. What direction is that going? I'm not trying to be cute. Up, okay? And it's on the left side of my graph, right? So what we're actually saying here is we're saying, okay, so this goes, as we're going to the left, this is going up. As we're going to the right, the graph is going down. Would you agree? Now we're going to put it into math language. Okay? So, as y goes up to positive infinity, just like it does on the y-axis here, x is going to the left. Y goes up as x goes left. That's true. And then I go to my other arrow, which I wish I'd followed by colors. Here, y goes down to negative infinity as x goes to the right to positive infinity. If you need to, don't just use the words, but if you need to do like what I'm doing here and literally write, you know, up, down, left, right, underneath, until you get the hang of the lingo, do that. There's nothing wrong with putting the words with, but don't just put the words. Because if you try to do that on the quiz, I'm going to be like, nope. It's like taking a Spanish test and you're writing everything in English. You can't do it. Okay? I mean, you could. It just won't work out well. And so, whenever we're doing these, all you're paying attention to is this. Okay, I'm going to lock you in on this. We'll actually finish these examples tomorrow because it's wanting you to do other things too. I'm not getting into that yet. We'll get there. So here, all right, let's get our first stuff done. And no, there is not a shortcut to writing this. Again, think English first, okay? This, that's just an arrow. This, as I got writing too quick in my, I'll start printing instead of cursivating because I can kind of blend the two together and it's hard to read sometimes. So I look, and I will give you a hint to make things go a little quicker too. We're always doing this. Your x's, you will always have one that is negative infinity and one that is positive infinity every time? So if that helps simplify some things, that would be helpful. And so I look and I go, okay, so I just got to figure out the y part. When I'm on the left side of my graph, as x approaches negative infinity, I'm going up, which is positive infinity. And as I'm going to the right side of my graph, my arrow is still going up to positive infinity. Okay, that's all you're doing here. And so the nice piece of this, like I said, I'm going to save C for tomorrow. The only other thing you've got to look at, end behavior, okay, check. Determine if it has an odd or even degree, because you've done the rest of this. Just look at the largest exponent. The degree equals 3. 3 is an odd number. Okay. My degree is 2. 2 is an even number. Okay. What we'll do tomorrow is show you how to just look at the graph without having the equation and still be able to tell me if it's odd or even, which is a really slick trick and makes things go faster with all of this. But I'm going to save that for then. So, Hardy, what can we do now? Nothing? No. Better than that. So, as we start this 3-2 assignment, you are fully capable. Dang, that's pretty good. Now, am I telling you have to do all 27 problems? You know me well enough. No. Duh. Okay. But can you do odds? Sure. If you want to go on the even route instead, I have fully worked out stuff for evens. Not to just copy, we know where that gets us. But if you want to have questions on things and look and go, okay, I want to actually be able to check fully what's going on, I'm happy to let you use that. That's fine. But otherwise, the odds are on the back of this. The odd answers are there. I double-checked last night. I think they're on. So if you need that, check those. But do some. Do a little of each part tonight. And that way, tomorrow when we get together